Hello, everyone. My name is Marcy Samuelson, and I am Marketing Manager for the Developer Initiative here at Oracle. Thank you for attending today's Tech Classroom, Deploying the Linkerd Service Mesh on OKE. Before we get started, I would like to review a few housekeeping items. The webcast console you are looking at can be completely customized. You can resize or move any of the windows that you have open. At the bottom of your audience console, there are multiple application widgets you can use. If you have any questions during the workshop, you can enter your question in the Q&A area and submit your question. We have a number of Oracle and Buoyant experts on the call that are ready to help you. If you experience audio or screen issues, please make sure the audio is turned on in the media widget or press F5 to refresh your screen. This webcast will be made available on demand after this live event. You will be able to access from the same link as the link you used to access this live event. Again, thank you for joining the Tech Classroom Deploying the Linkerd Service Mesh on OKE. This webcast will be presented by Charles Pretzer, Field Engineer at Buoyant, and Gilson Melo, Principal Product Manager at Oracle. At this point, I will turn it over to Gilson.
Thanks, Marcy. Very happy to be here today with my Buoyant friends to talk a little bit more about all the cool stuff we have been doing together. And as usual, we will use the first 10 minutes to talk about OKE, let you guys know what we've been doing on our side, and then the remainder of the presentation will be done by Charles from Buoyant. This is Oracle's Safe Harbor statement. I'm going to give you a few seconds to read it. Before we jump into Buoyant Linkerd's content, as I mentioned, let me give an overview of Oracle Container Engine for Kubernetes, also known as OKE. So why Oracle Kubernetes? OKE is a fully managed, scalable, and high available service that you can use to deploy your containerized applications to the cloud. Oracle Kubernetes is based on the upstream version supported by the Cloud Native Computing Foundation, CNCF. So that means no vendor lock-in, and also means that everything you have tested with Kubernetes on premises can also be ported to OKE without the need to re-architect it. So use OKE when your development team wants to reliably build, deploy, and manage cloud-native applications. Oracle's cloud-native services leverage a highly performant next-generation Oracle Cloud Infrastructure, OCI. The services can be categorized into application, development plus operations, and observability plus messaging. As you can see on this slide, we provide several cloud-native services that combined with OKE will give you a robust and scalable cloud-native service environment. For example, we have streaming services, which is fully Kafka compatible, logging services compatible with Fluentd, native monitoring, notifications, events, API gateway, infrastructure as a code that allows you to run your own Terraform stack in the cloud through our resource manager UI, for example, functions, and several other services. Plus, since OCI and OKE are based on open standard services, you're more than welcome to bring your own open source software that you're familiar with to use along with Oracle Cloud Native services. So what's Oracle doing in regards to open source software and community? Oracle is a platinum member of the Cloud Native Computing Foundation and a member of the Open Container Initiative Linux Foundation project. So we're very serious about using open standard services and supporting the Linux community in general. Oracle is the only major cloud provider to deliver and support a unified cloud native solution across managed cloud services and on-premises software, supporting seamless bidirectional portability of cloud native applications built anywhere on the framework. As I mentioned a few seconds ago, Oracle Cloud Native Framework is based on open and conformant CNCF standards. So again, no vendor lock-in, and applications built on that framework are portable to any Kubernetes conformant environment or any cloud or infrastructure. Let me give you an example. Applications running on WebLogic on premises can be easily containerized or put into containers, and then lifted and shifted into Oracle Container Engine for Kubernetes without re-architecting and rewriting any code. This makes the migration to public cloud very easy. Along with that, Terraform configurations can be reused across Oracle Cloud environments. They can be modified to be used in other cloud environments and also be automated with Cloud Resource Manager for Terraform stacks, for example, and so much more. So this slide just gives you some examples of what we're doing in regards to Linux and the open source community in general. Oracle's second generation cloud infrastructure, known as OCI, provides bare metal, virtual machines, containerized compute, GPUs for performance-intensive workloads such as artificial intelligence and machine learning, and a variety of cloud storage options like block, object, file storage, and archives. OCI offers a fantastic array of services for developers to build modern applications, and OKE, of course, uses OCI as the main platform for its services. Regarding to the framework and programming language options, we don't restrict our users to 1 or 2 programming language options only. So you have the choice to use any programming language and framework like Java, JavaScript, Node, Python, Ruby, and others. And you can use any DevOps tools as well. In addition to that, we provide a set of free tools like Developer Cloud Service for your DevOps framework. But you can also use the ones you're already familiar with, like Jenkins and GitLab, for example. This is the enterprise cloud you have heard of, providing an integrated data platform for the enterprise. This includes our flagship Autonomous database, but we also offer the choice of other databases like MySQL or Microsoft SQL Server. Finally, we provide several services to help you manage, secure, and monitor your own applications like Oracle Management Cloud and others. Okay, let's talk a little bit more about Oracle Container Engine for Kubernetes, OKE, and Oracle Cloud Infrastructure Registry, or OCR. OKE is a developer-friendly enterprise-ready managed service that runs highly available Kubernetes clusters with the control, security, and performance of cloud infrastructure, while keeping pace and compatibility with the CNCF ecosystem. For example, OKE supports Kubernetes Helm for easy deployment of Kubernetes apps and several other features like bare metal support for your worker nodes, along with virtual machine and HPC shapes, for example. Oracle Cloud Infrastructure Registry, OCR, is a highly available container registry service that enables users to easily store and share their container images. OCR allows users to push and pull images using familiar tools like Docker CLI, or pull images directly into their Oracle Container Engine for Kubernetes deployments. OCR is a Docker V2 compliant and can work with OKE and other container engines as well. So interoperability is assured with both OKE and OCR products. To recap, we have covered some of Oracle open source initiatives and DevOps solutions, along with a quick intro of OKE and OCR. Now, let's talk about pricing options. The gray shaded area on the left designates the functions that Oracle manages for the users, including an integrated registry, image store, and a fully managed container engine for Kubernetes. Oracle will manage the etcd and master nodes of the Kubernetes instance in a high availability setup for the customer. Upgrades to new versions of Kubernetes will also be supported in the Container Engine dashboard within the OCI console. It's very easy to upgrade your OKE masters along with your node pool servers. And you decide to do it when you want to do it to mitigate downtime situations. Users will manage the worker nodes that are set up by the managed service for that instance in their own OCI account and tenants. That's the shaded in blue above on the right. Users do not pay for any of the Oracle managed container infrastructure, the gray area on the left. This is a control plane that enables you to configure those services, maintain operations, versions, availability, etc. Users pay only regular fees for the compute, storage, and networking using in the data plane, the blue area on the right, where the applications will run and your data will be stored. By the way, did you know that some cloud providers charge you for the control plane for the master nodes and services? I'm talking about the free services that you see here on the left side, So OKE and OCR not only provide a reliable and robust environment, but also a very cost-effective platform for you and your users. I have a couple more slides left, so let's use them well and talk about some of the very unique capabilities that we have available for you. Like, how about using OKE with other Oracle services? Well, Oracle provides a service broker to make it easy for you to get your microservices talking to other Oracle Cloud Native services, for example. Oracle Service Broker is an implementation of the Open Source Broker API that you can use in the Kubernetes cluster to provision and bind to OCI services that your application depends on. It includes integrations with key OCI services like Autonomous Transaction Processing Database, Autonomous Data Warehouse, other Oracle database options, streaming services, and object storage service, with additional integrations on the way. The main key benefit of the Service Broker is reducing the complexity in the app deployment. So it's very easy to get your OKE microservice talking to other Oracle services. What about persistence? How to make sure the data is persistent with OKE? As you might know, applications can be categorized as either stateless or stateful. Containers are well suited for stateless apps, but require the use of external data stores for stateful apps. For example, stateless apps do not require persistence, they are easily redeployable and easily scalable, they can easily be containerized. And as an example of stateless apps could be a website that serves the same static web page to all clients. What about stateful apps? Well, they do require some persistence. They are more useful for complex use cases like an e-commerce website that keeps track of your cart as you shop, so it basically keeps track of your state. OKE provides servicing capabilities for both stateless and stateful apps, and as you can see here on this slide, you also have the capability of integrating your apps with Oracle Flagship's Autonomous Database and other storage services like block and file storage service, for example. Finally, here are some highlights of new features that I would like to share with you today. First one is Cloud Shell. Cloud Shell is a web browser terminal accessible from the OCI UI with several useful tools and utilities to install it, like Git, Java, Python, KubeCat or kubectl, Helm, Maven, Terraform, Ansible, SQL+, and others. Cloud Shell is also fully integrated with OKE and functions, so that means you can manage your OKE clusters and functions directly through the UI. We have also released some OKE aspects that are now available for our users, and there are additional options coming soon. Last but not least, pod security policies. They control operations that pods are allowed to perform on a cluster that you have created with OKE by setting up some security policies for the cluster. For example, you can use the pod security policies to limit the storage choices available to your pods, restrict host networking and ports that the pods can access, prevent some pods from running as the root user, for example, and also prevent pods from running in privileged mode, and other additional options. Excellent. Now that you know more about Oracle Cloud Native services in general, let's dive into Buoyant Linkerd slides and live demos to understand better how you can use Linkerd Service Mesh with OKE. Now I'll turn it over to Charles.
Okay, great. Thank you, Gilson, for that introduction. I'm really excited to be here working on this OKE, Oracle Kubernetes Engine cluster. We at Buoyant and the Linkerd team, more importantly, the community, have been working really hard to make sure that Linkerd works on every flavor of Kubernetes. And so when I heard that Oracle had come out with its own managed Kubernetes service, I got pretty excited. And so this is really a fun opportunity to show Linkerd working on OKE. So with that, I'll just jump right in. My name is Charles Pretzer. I'm a field engineer at Buoyant. all of my contact information is there. So if you want to reach out to me, you can send me a tweet or find me on GitHub. My Slack is at Charles. That's at slack.linkerd.io, and that's where the open source Linkerd community hangs out and chats. And you know, if you have any questions about using Linkerd there, come say hi. And then of course you can email me. So today we will go over, we'll do an overview on service mesh in general, talk about some of the high level concepts, why service mesh exists and where you can get value out of it. And then we'll talk about deploying the Linkerd service mesh on OKE, and I'll do an actual demo and walk you through it and show you how straightforward and easy it is. There's, in the industry, there's some concern about how difficult it can be to install a service mesh. And one of the really core design principles for Linkerd specifically is that the user experience is just easy and seamless and great. And so if nothing else, I want to show you that. But there's so much more that I hope that you all will be able to take away from this, including the just the value, the metrics that you're going to see, and some of the security features that are added by having a service mesh. And then I'll talk briefly about SMI, the service mesh interface. This is becoming a rapidly growing spec, and so we'll dive into that. And then we'll have time for questions and discussion after that. So let's just get started. We'll talk about the service mesh overview and some concepts. So what is a service mesh? When we've got a distributed system, we have all of these different pieces that are communicating with each other. And so part of the background that I have is I used to work with Oracle Commerce, which is a large J2EE monolithic application that's used by many companies for providing product catalog and order and user profile functionality. And so I started my career with this software and working with monolithic applications. And then as cloud resources became more popular and building distributed applications in the cloud, we really saw that there was a need for being able to manage all these different components that are communicating with each other. And so what we've got here is a very simple 3-service application that really gives you just the basic fundamentals of this is what a distributed application looks like when compared to a monolithic application, which all of the services or all the processes run within a single memory space. The reality of our distributed applications is that they're much more complex than just 3 services. For every service that you have, you usually have multiple instances of each service, which makes it adds complexity there. You've got to keep track of the number of services and make sure that those resources are being utilized effectively. And then we also have a number of those different services. So again, this is based off some conversations that I've had with users in the Linkerd community and customers as well. This is a fairly small application as well. We see that some distributed applications can have as many as 15 or 20 services or even more. And those are individual services. When you talk about the instances of those services, we begin to speak of many workloads that are running within this distributed application framework. So here we see what I like to think of as a more realistic version of a distributed application. We see that there is a persistent data store that this service X communicates with, and there's also an external API that this service Y communicates with. And then within the application itself, we see each of the services communicating with each other. And again, this is just an example. This may not be what your application looks like, but the goal here is to show you how things can quickly become complex. And in a perfect world, we can pretty easily, or we can begin to wrap our minds around that complexity and understand how the application works. But you know, these are computers, these are ones and zeros, and they tend to do things that perplex us every once in a while. And so when you get a distributed system with all this complexity and things start to go wrong or something unexpected happens, like your database begins to slow down or is getting a ton of queries and it catches on fire, so to speak, we need to be able to understand when that happens. And that's one of the value propositions of the service mesh, is to be able to detect when a particular request or branch of logic is failing, and we can begin to track that down through the metrics. And I'll show you an actual example of that once we get into the Linkerd demo. Another thing that might happen is your external API may become unavailable, and we need to be able to understand when service Y fails. So what that means, that could be a rate limiting thing, or the external API could just be unavailable. Their systems could be down. And so we want to be able to, in our distributed system, we want to make sure that A understands that service A understands that service Y is failing. And it may not be because service Y itself is failing. It's because that dependency that service Y has is failing. And then another thing that could happen is, you deploy a new version of some service, and I may be guilty of this myself, but sometimes you write code that just isn't very performant. And so in this scenario, when a new version gets deployed and things slow down, we want to be able to understand the impact of that, and we want to know how it's deviated from our baseline performance. And in this case, since we're talking about milliseconds of performance, we want to be able to ensure that our users have a great experience. And what I mean is the users of our application have a great experience, and so that when new code is deployed, it doesn't impact them negatively. So what we've seen here are three particular problems that can happen, and there are three of infinitely many problems that can happen inside of a distributed application. And the worst case is when one or more of those things happen at the same time. And this is where the service mesh is extremely powerful. So let's take a step back and look at that same simple 3-service application with a service mesh as part of the architecture. So Linkerd uses a sidecar architecture, which means that these proxies, which comprise the data plane, and there are two pieces to a service mesh: the control plane and the data plane. These proxies are now handling all of the traffic between the services. And so what we see in this diagram is our same simple 3-service application, but the services themselves are not communicating with each other, nor are they receiving any traffic except for traffic from the proxy. And this makes things very interesting, because now this proxy can give us a lot of interesting information about what is happening within the application. And so it's worth noting here that the question that I often get is, well, if I'm putting a proxy in, that means that I've got an extra hop and I'm adding latency. And sure, there is a bit of a trade-off there. I can tell you that the Linkerd proxy is built to work. It's built using Rust, which is a new programming language that is memory safe and highly performant, very C-like. Oftentimes folks think that we're using a different proxy, but we've written our own so that we can tightly integrate it with the control plane, which I'll talk about in just a second. But specifically in a Kubernetes environment and in OKE, what we have is within a particular pod, these proxies are injected as containers. And so the proxies are then routing traffic to the service containers within the same pod. So that means you've got local host communication within the pod. So latency is not a tremendous concern for the Linkerd proxy because it's written in Rust. It's extremely fast, extremely lightweight. And so adding these proxies to your services shouldn't be, it's worth thinking about, but it shouldn't be a major concern. So the data plane, if you can imagine that example of the more complex application, every service that we have is now going to have a proxy, and every instance of that service is going to have a proxy. So that's why we want to make it lightweight, so that it's not consuming too many resources, or it's not consuming resources more than you would expect. And again, it remains highly performant. So that's the data plane. It grows as your application grows, as the number of services grow. What remains constant, and I mentioned this just a second ago, is the control plane. The control plane for Linkerd runs as a set of services and deployments in the Linkerd namespace, and it provides functionality that configures the proxies. It also provides functionality for being able to understand the performance of the application. And again, I'll show you how some of that works. So the Linkerd control plane also has an identity component, which is used to distribute certificates to each of the proxies. And that becomes really, really powerful when we talk about using mutual TLS in a transparent manner. So just in that short conversation, or that brief monologue, I've talked about the observability, the security, and configuration of the proxies. And so this touches on a few of the core tenets of the Linkerd, well, service mesh concepts to begin with, and how Linkerd implements them. So let's take a look at those. The first is observability. That gives us the performance of the application, of the communication between each of the services. So what that means is we're getting success and error rates. If you remember back at our more complex diagram, if the external service that the external API that service Y communicates with it becomes unavailable, we'll start to see some error rates in service Y. We get golden metrics that are defined by the SRE book that Google has written. So we're talking about P50, P95, P99 latencies for for the communication between each of the services. And we can also get information through distributed tracing by instrumenting the services. So of all of these features that we see here, one thing that's really important, I'll talk about in the security piece, is that it's transparent, which means the developers writing the business logic don't have to add any logic to the services in order to enable all the functionality that we're going to see. The proxy itself encapsulates that functionality and provides those metrics back to the control plane so that we can see them. And the reason that I mentioned that now is because the one caveat to that is the distributed tracing. Specifically, if you're using open telemetry or open census, your services themselves need to be able to emit spans for distributed tracing. And so if you've not touched on distributed tracing, then I won't dive too deep into it, but just know that if you want to implement distributed tracing with any service mesh, your application code will have to be instrumented. But all of these other features that you see here don't require any instrumentation of code. And we'll take a look at how that works as well. Security, as I mentioned, is really a powerful piece of the Linkerd service mesh. When you install the control plane when I walk through the installation of Linkerd, I'm not going to specify my own certificates. For production environment, you would definitely specify your own certificates, and Linkerd would then use those certificates to distribute certificates to the proxies. So what you've got is a trust anchor and a chain of certificates that you manage. Again, when I install in development mode, there is a certificate authority that comes with Linkerd and allows you to get up and running very quickly. But the really interesting thing is, by letting the proxies handle all this traffic and manage the certificates, your application code no longer needs to do that. You don't have to write any extra code to get mutual TLS by default. And that's really important for industries like banks or telecoms, which are required by regulation to have secure traffic even behind the firewall for that east to west traffic. And there are other companies that I know who just by their own requirements, their internal requirements, that they want to have that same level of security for east to west traffic behind the firewall. So security is a very powerful piece of the Linkerd service mesh. On top of that, we have reliability, the third tenet, which is ensuring things like load balancing. When you've got requests specifically for gRPC load balancing, Kubernetes by default does not do gRPC load balancing. It does basic round robin load balancing to services. When you use Linkerd as your service mesh, it will inspect the traffic, and it uses an algorithm called exponentially weighted moving average algorithm. So that that's just a very long way of saying that Linkerd, the proxy, knows which instance of a service is likely to have the lowest latency, and it will send the next request to that instance. So if you've got 5 instances of service A, the proxy has the information that it needs to send the next request to the instance of service A that is performing the most, performing the best, or has the lowest latency. In addition to that, when we talk about reliability, we talk about retries and timeouts. The one CRD that comes with Linkerd is the service profile, and the CRD is a custom resource definition. And that's a very powerful tool used by Kubernetes, or offered by Kubernetes, for building your applications. But it's also very often overused. And so we limit the number of CRDs that we offer, and that one is the service profile. So the service profile allows you to define routes for your each of your services, and you can get per route metrics, and I'll show you what that means as we go through the example. The other thing is we can set retries and timeouts on each of those routes. So as we add new services or understand the profiles of each of our services, we can say this service I know is really fast. It can have a very low timeout. Or another service which maybe has to go and communicate externally or to a data store can give it a little bit longer timeout. So we get really granular control over the communication between services. And finally, we talk about traffic management when we talk about the tenets of a service mesh. And for Linkerd, that means using traffic splitting to route traffic to different versions of a service. So in our example, if you've got service A and it is at version 1 and you release a new service, so you've got new version, and we call that version 2, we can configure Linkerd, the proxy, to weight the traffic and slowly send it over to this version 2 while we make sure that there are no errors in version 2, that it's performing the way that we want it to. And this allows us to implement functionality like blue-green deployments and canary deployments. So those are advanced topics that I won't get into today, but for folks who are building out automated systems using DevOps practices, this is a very, very powerful tool, this traffic splitting. So with that, we've talked about distributed systems, why we need to be able to collect those metrics, why we want to secure them, the basic tenets of a service mesh. So let's jump into installing Linkerd on our OKE cluster, and we'll see how straightforward that is. Okay, so I'm going to jump over to another screen here. You can see that I have, this is a brand new fresh cluster. The only thing that's installed on it is all the things that, well, we see the Helm tiller there, but everything else is what OKE needs in order to run, which is basically what Kubernetes needs to run. So I use a number of aliases as I go through this. So don't be confused if you see strange commands. This PO alias is just short for kube control git pods. So again, I have a few of those, and it saves me from typing, and which more importantly, saves me from making mistakes as I'm going through these demos. Okay, so the first thing that we're going to do, and I've already got Linkerd installed because I use it every day. But if you are installing Linkerd, you want to get started, the best place to do that is at the Linkerd docs. And there's this getting started page. I'm going to run through this. Again, I encourage you to have a look at this. I'm going to run through this installation process as I go through. We've got our cluster. So let's look at, so far we have, look at all the services. We see that, again, this is just a brand new bare cluster. So there's nothing in here. As I mentioned, I've got Linkerd installed already. So if I type Linkerd version, and Linkerd, when we talk about installing it, there are two pieces to it. There's the Linkerd CLI, and there's deploying the Linkerd control plane, which then enables the service mesh in your cluster. So I've installed the CLI already. You can, again, find this in the documentation for getting started. It's just a simple curl command. The first thing we'll do is check the, and one thing I want to mention is the Linkerd CLI is meant to be, it's designed specifically to behave the same way that kube control does, or kubectl, or however you want to call it. And so when we do something like Linkerd version, it tells us the client version and the server version, just like kube control version -- short does. So very similar behavior. What we want to do now is, first thing we're going to do is make sure that we have the permissions available to us. The RBAC is configured properly on the cluster so that we can install the Linkerd control plane. So we'll run Linkerd check -- pre. You can consider this a pre-flight check for installing Linkerd, and as long as everything is green, we know that we're good. If you're curious about what it needs to run, we check Kubernetes versions, we check that we can create service accounts, services, deployments. And so again, this is for the basic implementation, installation of Linkerd. We also have a multi-stage installation, which allows you to break some of this out if you have tighter RBAC controls. Again, it's an advanced topic. We're just going to run through this installation pretty quickly here. So the next thing we want to do is, so we know Linkerd can be installed, so let's do Linkerd install. The interesting thing about the Linkerd install command is all that it does is generate the YAML that we can then go and apply. So I encourage you to have a look through this YAML so you can understand exactly what's being created. When I actually apply this file, we'll see all of the different resources being created. But in this case, we have some deployments, we have some services, there are some service accounts, it creates the namespace. So I will just go ahead and do that. One thing I want to tell you is that we're installing in more or less a developer mode, a kick the tires mode, if you will. There's also an HA mode, and oops, what that does is, we'll just bring this up. So when we install an HA mode, as you can see here, it enables HA deployment for the control plane, which means that we deploy 3 of each of the control plane components. What are those components? Well, let's install them and find out. So this is kube control apply -f with all of that YAML that was generated by Linkerd install. So we can see here that there are services and deployments and cluster role bindings, lions and tigers and bears, all kinds of different things being created here. Ultimately, what this is going to give us is, so if we look at all the namespaces in our environment, in our cluster, we now see that there's a Linkerd namespace. So let's switch over to that one, and we can see the deployments there. One thing I want to show you is that there's another Linkerd check command. We're going to run Linkerd check, but without the -- pre. What this is going to do is go through and look at the current state of the control plane to make sure that Linkerd is healthy and it's running. So we see that the control plane is starting up, the different components. Again, if we look at the deployments, we see that there are about, I think there are 8 of them. 9, and I'll talk about some of these, but for example, the identity is the component that distributes the certificates to each of the services. So here's a fun thing that we're going to do. Let's open up the dashboard, and we can do this immediately because we have Linkerd running. So let's make this readable. And one of the interesting things is that Linkerd, the control plane itself, is also using Linkerd. So we already have proxies injected in here, and we can see we're getting these metrics already as the control plane is communicating amongst itself for various reasons. But already we're seeing these metrics, which is pretty powerful. So let's go back to all namespaces. We see that there's an octopus graph that shows us the deployments, the services specifically communicating with each other. So this is all great, but let's see a real application running. So what I'm going to do is, we have a couple of sample applications that we have developed at Buoyant so that you can see Linkerd actually being used. So if you do, so it's we're going to use one called Emoji Voto, which is a gRPC based application, which allows you to see, it allows you to vote on your favorite emoji, which is a lot of fun. Let's see, I think I've got this URL right, but I may not. Let's see what happens. Success, good, okay. So let's take a look at our namespaces again. And we see that there is now this Emoji Voto namespace. So let's go there. Or we'll make that the default. So that'll switch over. We look at the pods. We see now that we have these applications or these pods that are running. Let's see the services that are available. Great. Let's take a look at the application itself. One thing I want you to notice right now is that each of the pods has one containers running. We're going to change that very soon. So we'll go service, web service, port 80. Actually, we have to do 8080. So we're port forwarding, and if I go to localhost 8080, I should see this emoji application. Great. And we've got a bit of a cheat here in the background. You'll notice that one of the deployments is this vote bot, and it is sending requests over to the web. How do we know that? I know it because I use this application all the time, but let's find some empirical evidence to show us that it's communicating. And the way that I'm going to do that is I'm going to inject Linkerd into this application. One of the features of Linkerd is a auto injection feature. So if I annotate, and we use annotations for this, so if I annotate the namespace emoji voto with linkerd.io inject equals enabled, and this is the magic. By injecting or annotating the namespace, And let's get the namespace so we can see what that injection or the annotation looks like. Oh, I told you I was not great at typing. Okay, here we go. So when we look at this, we see linkerd.io inject enabled. Great, that's exactly what we want. We look at our pods. We still see 1 of 1, but that's because we need to restart the pods in order for the control plane to pick up that annotation and inject the proxy. So we do kube control rollout, restart deploy. This is going to restart all the deployments in the namespace. And we'll take a look at the pods. We see that they're coming up. Interesting thing now is that we see there are 2 containers in each pod, and these are the proxies. And this should all happen very quickly. In fact, it'll happen so quickly that I didn't come over here quickly enough to show you that we're already getting metrics from this application. And so here's that empirical evidence I was telling you about. The vote bot is sending traffic to our web service. Our web service should be sending traffic over to the emoji service. So we're seeing metrics there already. The key thing to take away here is that we're seeing metrics already. The proxies have already begun reporting this information to Prometheus, and this dashboard can then display it. Not everybody likes to use a dashboard, so we can also use the Linkerd CLI to get these metrics as well. So let's just do Linkerd stat on the services in the emoji photo namespace. That should give us, pods, sorry. If we look at the pods, we should see it. There we go. Okay, so let's clear this out and we can run that again. So what we're going to see here is the same metrics that we're seeing on the dashboard we have available to us in the CLI. Dashboard's updating automatically. We can use the watch command to continue to get updates from this application. I didn't know. Oh, emoji, but that's why. Okay. Linkerd stat po-n emoji photo. So now we're going to watch, and we can see that as these metrics come in, or as the requests are being made, we'll see that the requests per second are changing, the success is changing, and you'll see that success is not 100%. And I won't dive into it today, but this application, as you might expect for a sample application, has errors built into it so that we can go through and debug some of the issues. So this is the fun part of what a service mesh can offer you, is that we can see that there are errors. We know exactly where the errors are happening. They're happening in this voting service. And we can then go in and debug them if we need to, or understand where they might be occurring. And this is, in the dashboard, this is the equivalent of what we call the Linkerd tap command, or sorry, status command. And so here we go. This vote donut is failing, and that went away way too quickly. I lost it. There we go. Vote donut, and that's the one that we baked in. Anytime somebody clicks on vote for donut, there's an error. And that's just part of the fun of how we built this application. One thing we can look at is the tap, and tap you can consider like TCP dump for your application or for your distributed services. And so what this allows us to do is to start just seeing all the requests that are coming in. So what I've got right now is this query that's being run to tap the pods. So any request that goes to voting from web in that namespace for this specific path, for this vote donut path, is going to show up here. And so gRPC status is unknown. This is the one that we know to be giving us errors. So we can change this a little bit. I'm going to show you how we can change it, but we're going to look at it instead of in the dashboard, we'll look at it in the CLI, the same tap output. And the part that I'm going to change is the path. So what this is going to show us is all of the traffic that goes from the web pod to the voting pod, regardless of path. So this should start to scroll by very quickly, because again, this is TCP dump. We're looking at all of the traffic. So here we go. We see that we've got the paths for star, for walking man, for donut, and these are all just increasing the vote counts for these services, so, or for these paths. So this is again one of the tools that we can use to debug our application. So very powerful, especially if you've used something like TCP dump before. And again, this gives us granular control. If I wanted to see just all of the traffic that goes from, let's see, all of the traffic that just comes out of the web service. Is it web? It might just be web. Yeah, so this is all the traffic coming out of the web deployment going anywhere. And so this, again, it can spit out a lot of logs, but it can be very useful in debugging issues. One of the last things I want to show you is that Linkerd also comes with dashboards, and we can see that our squid graph has changed here. So we see all of the services communicating with each other. VoteBot is our traffic generator, sending traffic to web, and that is then going to voting and emoji. So let's take a look at some of the Grafana dashboards that come with Linkerd. Whenever we deploy a service, we get these dashboards built for us automatically. So we can see that for this web deployment, we've got our success rates, we've got our request rates, and latencies that have been added. And this spike is interesting. This might have been, I don't know what caused that spike, but it's interesting, and we know that it's there, and we could drill down and debug it if we wanted to. The last dashboard that I want to show you is, as I mentioned earlier, Linkerd is used to monitor the control plane. Linkerd monitors itself. So we can take a look at Linkerd health, and this shows us the data plane telemetry. We can see the CPU usage for each of our proxies. We can see the control plane traffic. When we first started up the control plane, there was a lot of communication going on in between each of the services, and then it died down. And this is going to be traffic that, so we see Prometheus reporting metrics. We would also see traffic going to the identity service, which are the requests from the proxies for those certificate signing requests. So these are the dashboards. So there are a lot of powerful tools that enable the observability piece that I mentioned to you inside of the, when we talked about the concepts of Linkerd. So again, we see that the one last thing I want to show you is, oh, it's already up here, perfect. So we see when we're looking at the traffic, we see TLS equals true on all these requests. And this is because the proxies are encrypting the traffic when it sends the traffic out and decrypting the traffic when it sends the traffic in. So, or when it receives the requests from other services. So we know that all of the communication between pods is encrypted, and all the communication between the proxy and the service, the containers within the pods, is not encrypted. But that's okay, because it's really the traffic among the pods that we care about. So with that, I think I've shown you everything. We can jump back over to the slides here. So we installed Linkerd. I showed you the Linkerd observability piece, and yeah, I think, oh, one more thing before we go, I want to talk about the service mesh interface. Service mesh interface is what we use to develop our traffic split functionality. And the service mesh interface is a specification that was developed by multiple organizations, including the Linkerd community, Deus Labs, HashiCorp, Aspen Mesh. So and I'm forgetting a ton of names, but the point is there is a group of people and organizations that came together to define a specification for what a service mesh should deliver. And the goal of this is to be able to enable users to have, or operators to use any service mesh that they want, and then to build on top of what those service mesh emits, those metrics. And so, again, for the Linkerd community, our first use of the service mesh interface is for traffic management, for that traffic splitting that I spoke to you about earlier. And so, again, when we look at this conceptually, the service mesh interface defines a layer by which all participating service meshes can conform if they want to. And that allows us to build applications and tooling on top of that, because we now have a standardized set of information that the service meshes are emitting, and therefore we can build applications in a uniform way, which again, we're talking about standards and specifications. That's really, for me, that's really what open source is about. It's very powerful. So we will continue to build on this. We're looking at implementing policy through the service mesh interface, and I encourage you to take a look at the project itself. I don't have a link in here, but it's smi-spec.io, and it was recently donated to the CNCF as a sandbox project. So gaining traction, and I think it's going to be very powerful for building applications that integrate with your service mesh of choice. So with that, I will let you know that the Linkerd community is one of the most fun open source communities that I've been involved with. And it's great that we have partners like Oracle to work with us and who are enabling us to secure their cloud orchestration systems using Linkerd. So again, I want to thank Gilson for having me on today. If you have more questions, please come check us out at in the community. So that's on GitHub, slack.linkerd.io. As I mentioned, I'm at Charles there. And yeah, if you have any questions about installing Linkerd on OKE, I will gladly set up a time with you, and we can walk through it, and we can do it in real time. So again, thank you so much. I appreciate your time. I hope this was helpful, and look forward to chatting with you all online.
Thanks, Gilson and Charles, for this very useful presentation, and to all of you who attended our webcast today. This live webcast has been recorded and will be available using the same link you used to access the webcast. Please feel free to access the link in the resource list to sign up for another live event or access one of our other on-demand webcasts. If you have questions about what was presented today, feel free to email the presenters directly. When this webcast ends, you will be presented with a survey. Please tell us what you think so that we can make these webcasts more useful. Hope you have a great day.